It's a great pleasure to have Mihai Budiu here as our guest speaker. Mihai was a PhD student here at CMU, starting, I think, the year that I moved here in '97. And he worked with Seth Goldstein. And he has worked since then at Microsoft and VMware, and he now has a startup company. And he's going to talk about one of his recent papers, which is also the basis of his startup company.
Thank you very much. So this is a small room. So let's just discuss about this. So if you have any questions at any time, I'll be happy to answer them. So the title of this talk is DBSP, Incremental Computation of Streams and its Application to Databases. So let me tell you what this is about. So I have two pictures here. I have an oscilloscope, and I have a database. So DBSP is an acronym, and it's a pun. DSP is from digital signal processing, which is greater streaming computations. And DB comes from the databases. And databases is the database seminar. So you just put them together and you treat databases as a stream processing device. And it turns out that this is a recipe for solving one of the very interesting problems in database, which is incremental view maintenance. So DBSP in itself is a tiny language. It's a language which has only 4 operators, which computes on streams. The basic data structure is a string. And out of the 4 operators, I only show you 2. So 2 are still enough to do all of SQL and incrementalize all of SQL. The other 2 are if you want to do fixed point computations. And it's a Turing-complete language. It's an extension of the simply typed lambda calculus, but I'm not going to talk about it in these terms. Why DSP is nice? DBSP is nice is because it gives us a way of defining, given a computation in DBSP, we can say this is the incremental correspondent of this computation. And because we can do this, we also give an algorithm that takes an arbitrary DBSP program and generates another DBSP program, which is the incremental equivalent of the original. And this wouldn't be as useful if the language was purely abstract, but it turns out that any database query you can write in a modern language like SQL, you can translate to DBSP implementation. So by doing this, we can essentially incrementalize anything that we can write in a language like SQL. And I'll make this much more precise later. And if you really want to know about the details, this paper was published in VLDB 2023. But it's not just the paper. We created a startup around it, and the code is all open source. Almost all of it is open source. So on GitHub, you can play with it. There's a Rust runtime with an MIT license. There's a SQL compiler, which does this stuff. So, today, there's 2 classes of systems that process databases and streaming systems, and they're usually separate. But my prediction is because of this work, this division will disappear. And in fact, streams, databases, and incremental view maintenance are just facets of the same 3-dimensional objects. We used to look at this object from one side, but if you rotate it a little bit, you realize that they are very tightly linked to each other and inseparable. So even if this had no uses, I think the fact that we can think about streams in this way is a very useful tool. I hope to convince you during the talk. Okay, so let me tell you the setup. We have a database, and then we have a query. The result of a query on a database is a table. These databases are usually about computing on collections which can be written as tables. This is what the relational model is about. And databases these days can be very large. 1 billion rows is not unheard of. And also databases change. So let's say, you modify a database, changes tend to be smaller. The database accumulates many changes over time. Let's say this could be around 100 rows in each change of the database. And we'll show time going from left to right. Okay, so this is a different version of the previous database. And the database keeps changing. Databases live forever these days. They live in the cloud. And these changes, they have a name in database. They are called transactions. So database change in a very orderly fashion. You can really talk about the sequence of databases. And the problem we want to solve is we have a query, the database changes, but your query doesn't. So your query is applied to every version of the database, and as the database changes, you want to know what these results are. How do they change when the database changes? So the query is fixed. And databases have a tool. They already know how to do this. These are called views. And views, you can declare in SQL saying, create view v as, and then you specify a query. The query is nothing but a function. Turns out that SQL, for all its, I saw you had this seminar called SQL or Dead. For all its aligned qualities, SQL is actually a purely functional language. It's a very clean language which expresses pure functions of the database, and the results are the views. So we want to reevaluate this pure function over a changing database. And these are also, snapshots of the view. For each new database, you have a new version of the result. So what we want to do, and what incremental view maintenance is about not computing the view starting from the database, but computing the view's changes. Now, remember, in my previous example, this change is 10 million times smaller than the database. So if you can do this in word proportional to the size of the change, you get a speed up of 10 million, which is great, right? Why wouldn't you do this? So what we want to build is the new kind of query, which we call the Q delta, which is a blue query. The input to the blue query is the change, not the database. And the output is the change to the view. And if we can execute these blue queries efficiently in proportion to the size of the change, then we solve the incremental view maintenance.
Maybe getting ahead of stuff here. Do you use for joins with your blue arrows? No.
Yeah, the query is arbitrary, an arbitrary query. And anything you can write, including the recursive queries or mutually recursive queries. Is this fine? Should we move this? Okay. Okay, so what are queries? I'll talk about queries as being specified by query plans. As I said, queries in a language like SQL are pure functions. So they're usually composed of primitive operators. That's the contribution of the relational algebra of Todd's papers. You can specify everything by essentially composing very simple functions like selection, projections, joins. So I'm going to show some computation using boxes and data using arrows. But this you could write using lambda calculus. There's nothing special. I like pictures myself. Okay, so this is how I structured my talk. First, I will tell you what string computations are, and I will show you why they are relevant to this problem. Then, second, I will show you that databases are streaming systems already, even if you don't think of them as streaming systems. And then we'll define what it means to compute incrementally on streams. And then we'll talk about what these delta objects are. So I said, you can compute on deltas, but unless we know what they are, we don't know how to compute on deltas. And then I'll show you, argue that SQL can be implemented in this language DBSP that we have defined. And I'll tell you a little bit about our implementation. So this is actually a theory paper. I'm not a theoretician. I never wrote a theory paper before. I'm not a database person either. I got into this by accident. But I think the theory is the interesting part. Once you know the theory, the implementation is not as interesting. So I'm not going to spend this much time. But we could talk about this a lot too. And I'll be happy to have a follow-on conversation about it. Okay, so let's start with strings. What are strings? Think of them as infinite vectors. In this picture, the time goes from right to left. And I'm showing this as an infinite vector, which is not, obviously I can't display all of it. And strings are typed. Every value in a string has a specific type. And if you really want to be very precise, strings are just functions from natural numbers to whatever type the elements have. This function, you ask at time 5, what is the value in the string? And the answer of the function is the value of the string at time 5. And we use this notation with square brackets instead of function notation. And for now, fancy me, we require the data in the string to have a commutative group structure, which means we have a plus, a minus, and a 0, which satisfies some nice axioms. They have to be associative and commutative. And this might look like too much, but I'll show you it's not a problem in practice. All right. So just to remind you what groups are, in fact, I said this. A group is a data structure which has a plus and a minus. Every element has an inverse. And when you add an element to the inverse, you get the zero. So now let me tell you about digital signal processing. Anybody here has a background in DSP? Great, great. So what is DSP? DSP is about taking continuous signals and computing on them using discrete computation. So you measure the signal at specific time points. Usually you sample the signal, and then you, instead of computing on the complicated object, which is a continuous magnitude, you just compute on some numbers. These are analog to digital and digital to analog conversion. And it sounds like preposterous. How could they represent an object which has an infinite dimension using something countable, right? But there's now this fantastic theorem, which is one of the fundamental theorems of mathematics, the Nyquist-Shannon theorem, which says that if your signal is not too complicated, doesn't have too high frequencies, you can represent all of it without any information loss using those samples. Assuming you can represent the samples with infinite precision, but let's ignore that. And that's why CDs work. A CD samples the signal at 44 kilohertz. Your ear doesn't go even to 15 kilohertz these days. So here, everything you can hear is represented. So what this enables you to do is, instead of building very complicated analog circuits that compute from analog signals to analog signals, you can actually digitize the signal, compute using programs that we know how to do, and then convert back at the end. From the digital signal, you can recover the analog signal without any loss. This is a commutative diagram of mathematics, right? So it's a very precise definition of what we want to do. So now let's see a few signals. This is a signal that you don't get to hear very often. It's the silent signal, which is, remember, a signal is a stream. It's zero for all times. It happens to be the neutral element for stream addition. Streams themselves will form a commutative group, as we'll see. Okay, now let's assume that you have some operations that compute on streams. What I'll show you is streams will be double arrows. So you can compute the same way you can compute on numbers, you can compute on streams, right? And this is the composition of a few stream functions. The inputs are streams, the outputs are streams, right? You know how to implement this using code. Turns out you can implement many kinds of computations on streams, but we restrict ourselves to something called causal computations, causal, which means that to produce the output number 1, you are only allowed to look at inputs 0 and 1. And nothing behind. Then these objects can run in real time. So like playing a song in reverse, like the Beatles did in the 60s, right? That's not allowed. That's not a causal computation. Okay, so now this is the first stream operator I'm going to show you, and you will agree with me that it's a very simple one. It's called lifting. It's given a function within a scalar object. We just apply this function to every value in the stream. Right? So this is the input. This is the circuit, and this is the output. Looks pretty natural, right? And it turns out that because streams themselves are objects, they are functions, remember, from time to values. This is just function composition. Applying the function, lifting the function is just composing the function with the stream itself. Don't worry about it too much. Okay, here's another thing they want to do, and you do often with audio streams, you amplify them. Amplification is just lifting the multiplication with the constant. Right, so the input is a signal, the output is a signal where each sample is a little higher, and it works. You know, this is how this is used in. That's how I play my sounds through Zoom. This is how I make the volume loud.
What are you amplifying? Sorry, like what is C in this case?
Oh, C is a constant by which I multiply every value of the input stream. It's the amplification factor.
Can you do that by using a lifting function?
Yeah, it is the lifted function.
Okay.
This is the function, the C times X.
Okay.
And this is the function I'm lifting in order to, yeah. So what I'm doing here, I'm just showing you some examples of stream computation so we get familiar with them. There's another nice stream computation, is negation of a stream. You lift the minus. So I'm not showing the lifting sign, but essentially that's what you do. And this is really handy. You've used this a lot when you flew, because this is how noise canceling headphones work. They actually predict the signal because the signal has a periodic component They predict the periodic component, they negate it, and they subtract it. And if you can predict it perfectly, you get silence. You can get silence out of a very noisy environment. But it works. And this is a circuit, right? You essentially negate and add. This is the circuit that does this computation. The circuit on strings. Just function composition. Okay, now the second operator I'm going to show you today, people call this z mod to the -1, but when you see z to the -1, it's already delay. It's a very simple stream operator, but it cannot be represented as a lifted operator. So the way it works is given a string, it just delays the string by one value and outputs a 0 for the first value in the string. Very simple operator. You can see how you could implement this in software or in hardware, right? You essentially have to remember the previous value and output it when the next value comes. And for this, you need to have memory. And this is the only operator in our language which has memory. All the other operators are pure functions, and they operate as lifted functions. Okay, now let's build some other interesting circuits. We have two answers, but strictly speaking, what we do, we delay the input, then we subtract it from the signal itself. Yes, this is really a diff, right? So your current output is the current input minus the previous output, means minus the previous input. So this computes diffs, right? Remember, we want to do incremental computation. Turns out you can compute changes from a stream using a stream operator, which is a very simple operator. It has only 3 primitives. And we'll label this as D and call it differentiation. And this is actually the discrete correspondent of the differentiation of functions in the calculus. So again, given a stream of values, if you apply this D operator, you get a stream of deltas. Very nice. Now, second example, this is an even simpler one. This only has 2 boxes, a plus and a delay. Let's see if you can guess what this one is doing. Sorry. Right. I don't know how you did it so quickly, but so first of all, this looks like it's ill-defined because it's a recursive definition, right? You define the output in terms of itself. But it turns out that this operator has some very nice properties. You could write it as an equation, and this finds out the output is defined as a fixed point operator, technically. And for every input S, you have a unique solution for the output. You could see this as a system of equations, which is a diagonal form already, so it has a unique solution. You could argue this way. So the first output is the first input. Remember, here the first value you get is a 0. So the first output is just the first input. And in general, the kth output is the current input plus the previous output. And if you expand this, you get that any output is the sum of all the previous inputs, a prefix sum. And there was a language called Nessel that was defined here many years ago, in which a prefix sum was a primitive operator. Well, it turns out that you can define it as a stream computation. So we call this the integrator. And this is indeed the discrete version of the continuous integration, the indefinite integral in the calculus. So given a stream of deltas, the one we completed previously, we can reconstitute the original stream unchanged using this operator. Now, this I and D, as you would expect from calculus, they cancel out. If you compose them in any order, they are left to right inverses of each other. You get an identity function. And we'll use this property a lot. So this integration looks like weird. I mean, do I really have to understand calculus to come to this talk? Maybe, I'm a database guy. I don't care about this. Let me argue that integration is something that you see all the time. This is how you work. You are a streaming system. The data comes to you, my words come to you one by one. And what you do is you integrate in your brain. So you get these words, and what you do is sum them up. And you build a mental picture of what I'm telling you. So this is how all objects in the world communicate with each other, right? So it's not something that's esoteric. I think understanding integration is something very handy that you might find other uses for. And it's a way of explaining how the physical world works. All right, and now let me argue that it's very relevant to databases too. All databases are streaming databases. Claim number 1. All right, so let's take a database. What is a database? It's just a set of tables. And what is a transaction? A committed transaction is a change to the database, one or multiple tables. The transactions themselves, they have this beautiful property, I think was defined in the 70s, they are linearizable, which means you can put them in a total order. And what is this? This is just a string. So transactions form a string, number one, lesson number one. This is the order in which the transactions are applied to the database. Now the database itself forms a string, okay? So strings are not some simple objects like samples in a signal. The snapshots of your database form a string. They are just functions from time to values. The value is a set of tables, okay? And database number 3 is your database after 3 transactions have been applied. And there's a very nice relationship between these two streams. The database is the integral of the transaction stream. The database is just nothing but applying all the transactions you've seen so far in this order, which is nothing but the integration operator I described it. Okay, so this is lesson number 1. If you remember nothing else, this is still, I think, handy. It's a very handy way of thinking, and not only databases, you can think about distributed systems in the same way.
Where the database do that?
Okay. Okay, lesson number 2, example number 2 on how databases are streaming systems. Views are lifted queries, correct? So let's say we have this stream of transaction snapshots, database snapshots. Remember, what is a view? A view is just essentially applying a query. It's a function, a pure function of the state of a database. So the view at number k is the query applied to the database number k. But this is nothing but the lifting operator. So if you take the query as a function and you lift it, what you get is taking the database stream, and you lift the query, you get the transaction, the view stream. So views are streams, databases are streams, queries are lifted functions. So the database already do this. That's why I say they are streaming systems. Okay, so do you remember this picture? That this is the problem we want to solve. We want to query Q. We want to compute this query Q delta. So in this picture, there's at least 4 different streams. There's a stream of database snapshots. There's a stream of database transactions. There's a stream of views, view snapshots, and there's another stream of view changes. These are all streams, right? They all are infinite sequences of typed objects. And now let me show you how, thinking about database streams, we can define incremental computation and solve this problem. So any questions? Okay, so I'm going to just put together the pictures I've shown you so far. So this is a picture we've seen. The view is a lifted query. Just apply the query to every database snapshot. Now, on the left, I told you previously the database is the integral of the transaction stream. So I just compose these 2 diagrams. Okay? If you feed transactions, you integrate, then you lift the query, you get the views. And finally, let's do something symmetric on the right-hand side. We apply the differentiation operator. The differentiation operator, what does it do? Remember, given a stream of values, it computes the stream of deltas. So, but let's look now what we achieved. What we achieved is we start from a stream of transactions, we get a stream of view deltas. This is the problem we set to solve. This is the lifted incremental version of the query that we wanted to compute. This is the blue object. This may look trivial, right? I mean, I didn't tell you anything interesting. But the final thing is that if you read these papers on incremental view maintenance, which are 50 years old, actually nobody said the problem in this way. Nobody thought about the problem as a problem of streams. Everybody thought about what is the last change to the database. And I'll show you why this is a better way. So first of all, we have to agree that this is what we want to solve. People previously were trying to compute some kind of partial derivative of this query with respect to its inputs. And it turns out that in the relational algebra, you cannot do this in general. The operators are just not well behaved. But this definition is always well defined. This works no matter what your query is, no matter what the streams are. These are total functions, IND. They don't throw exceptions. They work for any values that form a commutative group. Okay, so this is well defined for any query. It is fully compositional because the inputs and outputs are both changes. So if you want, you can chain this. And I'll show you there's a very important consequence because of this. This is one thing I learned in computer science. If you have symmetry, you actually are probably looking at the right solution. Or the other way around, if you don't have symmetry, maybe there's a better solution someplace. Okay? So now, but I want to make a very, very important point. So your query is a pure function. This is not a pure function. This is a function on streams. Okay? The input is a stream, the output is a stream. When you implement it as a system, what it would look like a circuit with some memory. Where is the memory? The memory is in the integrals. The integrals have a delay. Remember, the delay has to remember something. The delays remember something about the past. And that's why we can now solve the incremental maintenance problems. Because these are not functions on scalar values, they are functions on streams. So you cannot solve this problem if you restrict Q delta to be a function, a pointwise function. But you can solve it if you think of it as a function on streams. So this Q delta is a streaming system. It's not just a function, which runs forever. Think of it as running forever. And it maintains state, even though the original query was not stateful.
What is the state it's maintaining?
Just the previous values.
That.
So, okay, so you can solve incremental maintenance this way. Just implement this system.
Yeah.
You essentially build the whole database, and that's the state you remember. Remember the whole database.
Yes, I forgot on the next slide, the box is cute. Oh, I got it.
So there's memory both here and here.
Got it, yeah.
But so, first of all, now we agreed on what we have to do. Actually, let me point out something else. This, actually, maybe I have another slide about this. If you just implement this, it will work, but you can gain nothing. You will do what database already can do. You build the whole state, compute, and then forget most of it. Now we want to compute this more efficiently. And now we will do some program rewriting. It turns out that for many sheets of this query, you can optimize this program. Now, these streams happen to form also a group, because they are chief functions from time to a group, so they form a group themselves. And these Q functions sometimes can be linear as functions within groups, even actually monoids, they are called homomorphic sometimes. If your function is linear, there's a very simple theorem to prove that then Q is the same as Q delta. So you can actually implement this without integrating and without differentiating. Yes.
When you say linear operator, you mean, so for example, a join, would that be linear?
Yeah, very good question. We'll talk about joins. Joins,
Right.
so linear operators have to have a single input.
Right.
Because the
So-
definition says Q of the single input must be, that's the definition of linear.
So when you say most relational queries are linear, like these are like smaller, like
So filtering, selection,
Yeah.
applying a function, and
Projection.
well, projection, they are all linear.
okay, I'll
No. Joins are not linear, they are bilinear.
yes.
They are almost linear, but they can be done efficiently too.
Actually, would aggregation?
Aggregation is a very funny one.
Yeah.
Some aggregations are never linear in the strict sense.
Is I'll
That's a very nice point, aggregation. The problem with aggregations is the output is no longer a collection. When you aggregate, the collection result is a scalar. That part sometimes is linear, like for plus and count, sum, average, standard deviation, they are all linear. But mapping the last value back into a collection, that transformation is not linear. If you try to write the type system, you'll see immediately that it doesn't work. But that part is cheap. So we can do even nonlinear parts. So I'm just saying if it's linear, it's trivial. I didn't say if it's not linear, what happens. Okay. So no state is required for linear queries, and most relational queries linear operators. So what is linear? Think of linear as shardable. Okay, so if you can split the data into parts, compute separately, and then join the results somehow, then the query is linear. So in terms of distributed database, that's what linearity is. By the way, this is also very tightly related to linear logic. So I remember one of the last courses I took at CMU was linear logic from Frank. So
Is it a good course?
yeah,
Okay.
I
getting grades. Say.
audited the course. I didn't take
Oh,
it. Yeah. There's no persistent record. Now, this is actually, every time I look at this, I'm amazed it holds. This is a called chain rule. Yes.
Can we go to the previous slide one more time?
Sure.
Because you eliminated those two operators pretty easily. Although what that implies now is that the lift of Q is happening on a transaction type stream rather than database type stream.
Excellent point. So queries are defined to compute on tables, but these are not tables, they are changes. But changes, what are changes? I didn't tell you. We have a section for that. Yeah, but it's a really good point because changes can be negative, whereas tables cannot. But we still have to solve. Excellent. You caught me that I was trying to. Okay.
Deletion.
Yeah, I'll show you. It works perfectly for deletion. For now, trust me, but I'll show you how. Okay, now this is an amazing rule. This people in PL call this structural induction, which says that what it means is you have a query which is a complicated query, you can incrementalize each piece and compose the result. Okay, so this means that if you know how to build the incremental version of your primitives, then I can incrementalize any query you can write for me in this language. And this is the whole proof. It's a proof by picture. It's amazing that it's so short. So this is the top line. What does it mean, Q1 composed with Q2? It means apply Q2 after the Q1. And what is delta? Delta means just put an I in front and the D out. That's the definition. Right? And now what we do is we take this middle arrow and we insert a pair DI, which remember they cancel out. And now there's a fundamental thing in mathematics, function composition is associative. This is one of the things we rely on a lot. Then you just regroup, and this piece is Q1 delta, and this piece is Q2 delta. So this is why it's so important to be compositional. That's why it's so important for the inputs and outputs to be deltas, because then the chain rule holds. In traditional incremental view maintenance, people would think of the view as being the output, not the delta of the view. So that's why they didn't have this rule. Okay, so this tells you if you have a Q, in order to compile it down to Q delta, you decompose the Q into a composition. This is what any SQL compiler already does. And if you know how to incrementalize this, then you get the incremental version of the query. And moreover, there's something else it tells us. If you don't know how to incrementalize one of these, you can always use the brute force approach. Okay, so incrementalize the whole query plan. I have this bizarre new operator I call the user-defined function or something. Fine. Integrate before the operator, apply the operator, then differentiate. We can do anything. All right, so you asked about joins. This is joins. And this is a complicated slide. It teaches you several tricks. So this is the incremental version of a join. Actually, let's take a Cartesian product. It's even easier than a join. So it's a Cartesian product with each set. The incremental version, what is it? Well, you integrate each input, has two inputs, right? And you differentiate the output. That's just the definition. And this is how it can be implemented, optimized. This looks very complicated, but if you spell out this diagram, I have the spell out of this diagram, it will look very familiar. It's something people in database call the delta. So I'm only doing, what I'm doing is I'm just translating the data rule to work in circuits, on these DBSP circuits. So by the way, many of these results, they are all very well-known results. I'm just re-proving them using this framework, and this is a very healthy thing. If the framework couldn't accommodate all the results, it'd be useless. So it very cleanly integrates all these results. So this is how you do an incremental join. You actually do it using 3 joins, and let's see why there are 3 joins. Let's see Cartesian product. So let's say this is one of your inputs, and this is your other input. And what you do is you add a delta to your left input. What do you have to do? So you already computed A times B. This is A times B, the previous one, right? So you have 4 green A's and then 6 B's. This is the previous result that we had. So how do we compute the new result? What do we have to do? Well, we have to combine this new element with every element in B, right? So we get an extra row in this matrix. So how do we do that? Well, the way we do it is we take this delta A and then we integrate it. And here, what we have is the full collection A. This is actually the previous, it's delayed by 1 step. This is what A used to be previous. And now we take the new B and we combine it, actually, no, we take the new A and we combine it with the previous B. I should have described it on the bottom. This diagram is completely symmetric. Okay, so whatever is new in A, we combine it with the previous B, and that's how you get this row. And it's symmetric. If you add a change to B, you have to combine the new B with everything that was known in A, and then you get a new column. And then you have to combine the two things together as well. This is the delta row. So why is this better? I instead of having one Cartesian product, I have three. This looks like I made it worse. But it's much better because the inputs to all these three, each of them has at least one input, which is a delta, which is, remember, is 10 times million smaller than the original. So this, although it has much more work to do, it's much more efficient. Yeah.
Does that mean there are cases where incrementalizing the computation is more expensive than just rerunning from scratch?
Okay, so the question is, what? So you're asking about the cost of incrementalization. Can there be queries in which this plan is more expensive than the original plan?
Exactly.
Yes. Well, so we can show that for all. So the answer to this question depends on your operators. So we have to look at each kind of operator. For all the operators that show up in SQL, we can do them pretty much more efficiently. The speed up is the one we expect. Size of the database versus size of the change.
Yeah.
But there are operators, for example, there's a rank operator where you label each row with its position in the query. There, if you insert a row at the beginning, then every row in the output is changed. Okay, so your output delta is big. You cannot do any better than this. Now, in the worst case, the asymptotic cost is the same as the original, running the original query plan, but it's no worse.
Yep.
And then you have to look at every intermediate result you produce. If an intermediate result is big, then everything after that might be big. But if you, for well-behaved queries, this works very, very well. Okay, so now the questions you asked, what the hell are deltas? So the definitions that everything I showed you so far, all the theorems, if you look carefully, they will require a commutative group. But databases, they work on sets and multisets, which are not commutative groups. For example, there's no negation. What is negation in a database? Well, this is another trick, which is at least a 25 years old trick, which is, in general, if you can't solve a problem, why don't you generalize it? Make it harder. Sometimes the solution to the harder problem is easier. And it turns out that you can embed tables into another data structure, which is called the Z set. One of the people call them Z relations. And the Z relation is nothing but the table plus an extra column of weights. Mathematically speaking, these are functions from whatever type you have here to integers. And they are functions with finite support, which means that they have a finite number of rows, these tables. But the point is they are very simple mathematical structure that we can reason about. Now, this table, what do the weights mean? The weight will tell you how many times does the row belong to the table. So this row shows up once, this row shows up thrice, and this row shows up -1 times. Come on, man, I can't do negative numbers. Who can think about that? What is a table with a negative row? Well, you think about, debits and credits. Think about tables in the same way. It's things that shouldn't be there. This reminds me of a joke. I don't know if you know this joke. So they asked 3 scientists, the following riddles. So 2 people come into a house, the house is sealed, and later 3 come out. So what does this mean? So the biologist says, oh, obviously they multiplied. Another guy says, the physicist says there was somebody in the house previously. And the mathematician says, and one more will go in and the house will be empty. So that's how you have to think about this Z tables. So Z sets, they are actually a very nice data structure. First of all, because they are functions to a commutative group, they are themselves from a commutative group. When you add 2 Z tables, just match the rows and add the weights. And if something has a weight of 0, it just disappears. Positive weights means the elements are added. Negative weights means the elements are removed. And they also can represent sets and multisets. A set is nothing but a Z set where all the weights are 1. And multisets, which I use to SQL compute on multisets, is a table where all the weights are positive. And because Z is a group, as I said, they form a commutative group. So now, if we define all the operators in SQL to compute over weighted tables, then we solve the problem. And it turns out we can. right? So don't try to read this table. I made it on purpose very small. What I took here is all the relational algebra: selection, projections, joins, Cartesian products, set intersection difference, union, and I showed them how we compute them using Z sets. Okay. Yes.
I would like to like Z sets. The inputs are Z sets, right?
Yeah.
Yeah.
So if you restrict the Z sets to be positive,
Yeah.
you get the traditional SQL implementation. If you allow them to be negative, you get our implementation. And many of them have a distinct. So the distinct is the funny one. The distinct will throw away everything negative. And that's, for example, how you do accept. So set difference, if you subtract the weights, you might get negative weights. But using distinct, we'll throw them away. Yes.
Is it like the sigma function which turns everything greater than 1 to 1 or no?
Well, it's a discrete function, yeah.
So it does do that.
Yeah, you could say, but it's only 0 or 1.
Mihai, do you deal with outer joins in a special way or as a composition of some of these primitive operations here?
Yeah, so outer joins, you rewrite essentially using joins and the anti-joins. Anti-joins are not technically in the relational algebra, but they work very well. So it's a join union with some anti-joins. So you can do it, but this slide is only about the relational algebra. But they can be done. And correlated queries, you decorrelate them and then you apply the algorithm to the decorrelated version of the queries.
So this distinct is not, you said it just returns everything that's where the weight is exactly 1?
It will truncate all weights to 1 and then will remove things with negative weights.
What the weights here?
The weight 0 means the object is not there. So think of it as not existing.
Okay, so how do you handle the aggregate count distinct?
Okay, so the question is, how do you do something like count distinct? Well, you implement distinct and you implement count, and then because of the chain rule, the composition turns out to be correct. Now the question is, how do you do distinct incrementally, maybe, and how do you do count incrementally? So to do distinct incrementally, I actually have a slide about it. I see if I can find it. You do a trick very similar to the join. Okay, so in order to do the distinct incrementally, you integrate the input. So you maintain the full collection. And now if a new element comes, you see if it was already in the input. And when adding this element, the weight changes from negative to positive. It means this is a new element in the output, so you emit it to the output. If the weight changes from positive to negative, it means you have to remove it from the output. So your delta will depend on both the new element and the previous integral of the input. Okay, so
again, then the integration is very expensive.
Okay, so question.
State or something.
Okay, so is integration expensive? Well, what do we measure? So integration is append, really, right? So the question is, there's two costs. Let's not confuse them: time and space. So we can do integration in essentially, log n time, or even O of 1, if you think of it as append. Databases do append in O of 1 time, right? When you append the rows to a table, they don't, have to scan the whole collection. Integration is no different. But the space, you have to keep the whole collection, yes. And incremental view maintenance is a trade-off between time and space. What you're getting is fast time, but what you're paying off is big state. The space could be much bigger than maintaining the input collections themselves. Because if intermediate results are very large, you have to hold onto those. But there's something else too, which I didn't say this clearly. What I'm incrementalizing is not a query. What I'm incrementalizing is a query plan. There are many equivalent programs you can write for the same query. And some of them might be better because they might keep less state. But the question is not how big is the state, what is the cost, the time cost to operate on the state. And addition for integration can be done in constant time or logarithmic time if you want to be very finicky. And then for distinct, let's look again at distinct. When you have a collection that you change, you add or remove an element to the input. The only thing that can change in the output is this element itself, right? So if the elements that existed already that are not changed, they won't change in the output. So this is the only thing you have to scan. So if you use a hash table-based implementation, you can check, is this element already there in O of 1, and then you remove it or insert it. So yes, you pay in space, but you get 10 million. 10 million times in time is a good trade-off. So again, this is defined recursively on the query structure. Yes.
So 10 million for all kinds of queries. So I know you only showed one when there was just a join, but so this is very good language. Like, can it extend it to all kinds of queries, or no? Is there a limitation?
So the question is, when can I claim the speedup? The speedup I am claiming, I didn't put the formula, is the ratio between the size of the database and the size of the chain. So now, if you can make up, you didn't tell me what your primitive language is. Remember, this DBSP says you give me a functional list. Right? Now, if these functions come from SQL, I'm showing you how to do all of them efficiently. But you can invent a bizarre function on collections that I don't know how to incrementalize. And for that, we'll have to take a look. But you have to establish the base language. This is a lifted language.
Yeah, they won't be able to do it.
But all SQL, yes.
I don't forget when the stream SQL stuff made it into the standard. But like Kafka stuff has that. We can't do that.
Well,
The things would be like it's like a continuous query where like you have like the moving average and then you're emitting results every like minute.
yeah, we actually do that. Our
You
program
can-
does that. Yeah, so we actually built a continuous query engine. That's what we built
Okay.
based on this query. Yeah. Okay, and many operations require, so all these other operations, the red ones are linear or bilinear. So they are all efficient. The only one is the distinct. And you can do group by. Group by is linear. Unnest, which is the inverse of group by, is also linear. Aggregation, many aggregations are linear. You can do even mutual recursion, much more than SQL standard allows. So we have written a spreadsheet in this language in which we evaluate recursive formulas in a very large spreadsheet.
Maybe get ahead of ourselves. Can you support out of order incremental updates? Out of order screens.
Well, we'll have to talk about what it means to be out of order. But that's a very nice and rich topic
Yeah.
that we can talk about. I only have 5 minutes. I don't know if this is the right time to talk about. But we have a meeting. We can talk about it one-on-one. So this engine actually has at least 3 personalities, and one of them is stream processing, and we do out of order stream processing using several tools. We have as of joins, for example, which allows you to do time travel queries, and we give you an annotation which says there's a bound on the out of orderness. And in that case, we actually have an algorithm to garbage collect. We can say this part of the state will never influence any possible future output. So we can compute queries on infinite collections using finite memory.
Yeah, that's how they're both. Like there's the software model, there's like the NIAD model, there's like the old school Microsoft incremental UVM. I'm just trying to figure out where you think fits in. Sounds like you do everything.
Yeah, NIAD can do everything too.
Yeah.
This is a simplification of that model.
Got it. Okay.
So you said you had this causal, right? That basically the output for I dependent on I or this, right?
Yeah, this means essentially we want to run in real time.
So if things arrive out of order, it's it's no longer causal.
Logically, it's causal.
Well, the system is causal because when you will tell us what the change was, we will tell you what the output is.
The output of the views are burdened as well. You can update the old version, but you got to add an order update. That's the semantically still correct.
Yeah, the semantics we guarantee is the following. Given a sequence of transactions on the input, after k transactions, the kth view will represent the state of us applying the query to everything you've seen so far. That's the guarantee we give you. And by the way, this is a spec. This is the specification of what we have to implement. So very, very, I mean, maybe never in your life, only if you're very lucky, you'll have a spec which is one line long. Right? You realize how powerful it is. You know, all the testing that we do, we can take any arbitrary query, we run it non-incrementally, we run it incrementally, and now we can compare the results. So given the semantics for the queries, we have a semantics for this what we have to achieve. So so math is really powerful. Okay, so this is the algorithm to translate an arbitrary query to an incremental circuit. Given a query, the first thing you do is you lift it. So this just will compute on streams. Then you incrementalize it trivially by putting integrators in front and differentiators at the back. For every input, it's just a syntactic transformation. Then you apply this chain rule to simplify things as much as possible. This algorithm is deterministic, doesn't have any heuristics. You could say it's confluent in PL, so no matter which order you do this, you will get the same result. The complexity of the algorithm is the size of the query. That's why it's called structural induction. So it just works. Now this is an example. So then in this example, we take a query which has two selections, two projections, a join, and a distinct. So we start, this is the query plan. Okay, any query planner will give you this. If you choose your query planner, I don't care what it is. Then we lift it. Okay, so the first thing we do, we put arrows in front of everything and we make the arrows double because these are strings. Syntactic transformation, right? We just apply the operators to every value separately. But this query is not equivalent to the other one. It's computing on different kinds of objects, streams, not scalars. Then you add i's in front and d's at the end. This query again is not equivalent. This is the incremental version of the query. It has this property that if you look at the end and integrate all the changes, you get the same thing as if you started with the whole database. And now we optimize. This is the previous image. We apply the chain rule. And by using the chain rule, essentially what you do is you put a delta to every operator. So every operator in your query has a delta. Right? So, and the integrators have disappeared. So everything has to be incrementalized. And now some of these are linear. These two are linear. So the delta just goes away. And we are left only with two deltas, the distinct and the join. And the join I've shown you, the distinct I kind of have explained to you. And this is the circuit you get. This is a program, right? And it's very well specified. The join uses a slightly simpler expansion with only two joins. But this is the incremental circuit that corresponds to the original query. And we have a compiler which does this. And we can do a lot of stuff behind the relational algebra. We can do mutual recursive views. This is a spreadsheet on the web. You can go to this address and play with it. So you can write formulas, and there's a billion-cell spreadsheet. It takes advantage of the sparsity. You can see all the code. As this is briefly alluding to the fact that you can do finite memory computation on infinite streams. And so this paper was rejected when it was first written, and they said, you didn't do this. And I got really upset. So we had a
Rejected by who?
pods.
Yeah, there you go, right there, yeah.
So we had a postdoc who was a whiz in stage child in formal verification. So in 2 weeks, he took all the statements in the paper and he formally verified them mechanically using the Lin theorem proof. And this is published. You can verify all of them. It's only 5,000 lines. And it's trivial because the objects that we deal with are all very simple objects. They are just functions and finite groups. So it's a very naive theory compared to what other, you'll see there's much more complicated theory people do, but this is very, very simple. And then, we were researchers at the time, but the lab was kind of shutting down because the company was acquired. And we got some money, we got $6 billion from some venture capitalists. So we decided to build a company. And this is our product. We have this incremental view maintenance engine, but the foundation is all open source. So we publish the incremental versions of all the operators in the Rust library. There's about 80 of them. It's much more than you would expect. But the SQL is also an insane language. It turns out most of the complication is getting the data from the outside world and to the outside world. And, this is my message. If you build a database, the inputs and outputs should be Z-sets. So if you have a database, there should be a service saying, I want to register this view, publish the changes to the view as a stream of Z-sets. So people build this change data capture stuff and garbage, and it's insane how complicated it is to just find out what's new in a database. That should be a primitive the database offers. And this is very, very complicated.
Everybody should publish Z-set, but nobody does, right?
Nobody does.
Yeah.
So, and actually, this is our hope. because this algorithm actually I think is trivial. So any company could take this and implement it and put it out of business. But databases today, they don't understand negative changes. Yeah.
Aren't Z sets likely just another SQL query? Can't you do like counts and convert like your actual data and add any policies, etc.?
Okay, so the question is, can you implement computations on Z sets using relational algebra?
So can you create the Z set version of a non-Z set relation database using SQL?
Yes.
That's what we did
Yeah.
in our startup.
Yeah.
But the problem is the data structures used by database today, they don't have room for this extra weight. Many algorithms will actually become simpler. Even in data lakes, Delta Lake, for example, the way they do changes in data, they are separate objects. They don't have to be, they could be the same object. Many things could be simplified using Z sets. And that's our hope. Because I realized when I was a grad student, I was afraid people would steal my ideas. Today, I know that I have to beg them to listen to my ideas. So database, we have maybe 10 years before they will implement this. And by then, maybe we could survive and I don't know what will
So you're
happen.
basically doing like running queries to get the Z sets out. And that's your change data capture.
Oh, here?
Yeah.
So this depends on the input. So in things like Kafka, you have a tail of the log or CDC.
Yeah.
In things like Snowflake, they have notions of streams. You can get some of that. So it really depends. You have to do one of a kind. There's a lot of complicated code. And with unspecified code,
Yeah.
this is a nightmare.
Of course.
So when you're punished, that's what you get to do in our company. So you can try it online. We have you don't have to install anything. You can go there and type some SQL. I won't say it's perfect. It's based on Apache Calcite, so Calcite has limitations. We have limited resources, but a lot of stuff works very well. The code is there, and we have a bunch of social media. So let me tell you 3 ideas that I told you today. Even one of them, I think we might find useful. First of all, systems are not static objects. They are streams of snapshots. If you think about systems as streams of snapshots, this might simplify some of your problems dramatically. Second, incremental view maintenance is a computation from changes to changes. If you formulate that way, it becomes much easier because it's a compositional and the chain rule works and you can just do it. Now finally, Z sets are a richer data structure. They are still tables. You can implement them using B-trees and everything. But they can model both negative and positive changes. And databases today cannot handle negative changes. If you read AVM papers, you'll see, we model this is the negative part, this is the positive part, this is the updated part. No, you don't need that. It's only one Z set. All 3 of them are modeled by one data structure. Okay, so that's I ran over my time. Awesome.
That's great. Fantastic. Let's thank the speaker.
Can we see the optimization you did earlier for the query example that you were given?
The plan wasn't optimized, but you mean how the plan was transformed?
Yeah. Oh yeah. Why is there no z-1 on the top part? How did you optimize the join delta?
Oh, so the join delta has, this is the unexpanded join delta, which has 3 integrators inside. Each of them has and here, see, this is the final version, has 1, 2 integrators. Each of them has a delay inside.
There's an integrator and then there's history as well. And I'm looking at that z-1 in front of the bottom integrator. No, on the left.
There is no.
Yeah.
Oh, I see. So this turns out that integrated file by z-1, you don't have to do anything special because the you can tap a different wire in the integrator, and that is already the z-. Let's see if I can show you the. But what about what do you want to ask about?
I just didn't understand it in the first one.
So there's usually integrators in the plans are followed by a z-1 because you want to look at the previous version of the collection when you compute the next one. And that's what the delay is. And if you look at this circuit, the output is the current version of the integrator, but if you tap this line, this is the same as the integrator followed by a z-1. So that's free. It's free. Yeah.
Seems like the query plan that you choose has a very big effect on the space.
Sure. True, like in any query engine.
Sure. So I was just wondering what your plan is for the query optimizer.
Well, I am happy to compile a plan you give me, so I haven't had any time to think about this.
So just use a normal query optimizer, just incrementalize that.
Yeah, so I don't want to get into the business of writing a query optimizer. I'm busy enough as it is. But it's a good question. It's a good research question. What is the optimal query plan for incremental? You have a question?
Yeah. So, yeah, so sort of seems like a lot of memory could be used, like especially if you have large, if you have integrations all over the place. Like, what do you have a comparison with how much memory you'd use in a normal, like execution engine?
Okay, so the question is how much memory do you use?
Yeah.
And it's actually a very good question because this technique, the bigger the data, the more the speed up it. Correct? So if you have petabyte size data, that's when you have the big winnings.
Well,
On the
it's petabyte size ball chain.
yes, that's the
You
assumption.
get big changes then.
And you won't have petabyte changes. I guarantee
Yeah.
that. So the question is, it depends on the query, the query and the plan, how big the state is. Actually, this query engine we have right now is multi-core, but it's still single machine. The parallel is done to an exchange operator, so we know that will work across machines, but we haven't built a scale-out version yet. So this won't work for petabyte size queries yet.
So I guess my question really was if you have for the more complex queries, like what are you seeing? Obviously this would be really good for training, right? But databases generally have optimizing the query. So relatively simple thing. For more complex things, how like
So we have customers that have 50,000 lines of SQL. So I didn't think people could write this much SQL. So it has to work fine. So this customer has a 60 machine Spark cluster, which does the following thing. It starts running the views. It finishes in 20 minutes, publishes the views, and then starts again. It takes 20 minutes to recompute the data using 60 machines. We can do it in 1 second. Okay, so latency from a delta to the output is 1 second. We can't ingest that into the Delta Lake. Delta Lake has problems to ingest small changes. But our engine can be much, much more efficient. So this for this customer. But now you can create, really badly behaved queries if you want. So
yeah, I guess I should have what the 50,000 lines people made of so 1,000 joins.
yes, they have. We have a file for 150 joins.
And views of views of views of views of views.
Oh yeah.
The joins are not a problem. They also got joins really well.
Generally anywhere with. Okay.
So you need integrators in 3 places: joins, distinct, and some aggregates. Actually, for all aggregates for each group you need, because you need to update the count. This is it, essentially. But it's more complicated because there's window queries like over. Some of those we implement using integrators to. You can define very complicated languages over nested collections, and that's why we have 80 operators. Right?
I mean, we're recorded, but like, be interesting how your paradigms like materialize.
Yeah,
He's a co-author, but
okay. So the question is Materialize. Materialize is a very interesting company. So it was created by Frank McSherry, who was a colleague of mine at Microsoft Research in Silicon Valley. I've known him for more than 20 years now. And
you were fired with him.
Yeah, we were fired together. Yeah. So he built this theory called differential timely data flow and differential data flow. So initially we created a language called differential data log, which runs on his framework. And we built a product at VMware, which does exactly this for a specific use case. And then we deployed it. And we realized that nobody wants to learn data log. So if you can't put it on LinkedIn, say, I know this, engineers don't want to touch it.
You never took a database course, did you?
Which one?
Anyone. The data log, nobody uses it. We tell them.
Yeah, well, so this way decided to do SQL.
Yeah.
But by trying to formalize what differential data log does, that's how we came onto this theory. And this is actually a simplification of what differential data flow can do. So what they allow, essentially fundamentally, is they allow out of order changes to the inputs. They can say, I change the input that I gave you yesterday. And what this does in their framework, everything since yesterday will be corrected. They will publish corrections to all the views they've shown. Now, we thought in practice, few people want to do that. And we get rid of a one-time stamp, and the theory is much, much simpler. So the main problem with differential data flow is nobody understood what happens. And this is because Frank doesn't like to write papers and learn. When you publish to a community, you have to learn their language. And Frank is not a database guy. He's one of the smarter guys I ever met. But he never made the effort to explain how differential data flow works. So work was completely ignored by database people until maybe they founded the company and they showed it works. Now, Materialize has $100 million in funding, and I'm very upset that they're not more successful. I think there's a lot of room for both them and us in this market. They look like Postgres, we look like something completely different. Whatever Calcite can do, that's what we do. We're tied to that. But I don't understand why they're not more successful. I expect they would be more successful. But the way you package the product is very important. And I think they chose too narrow a market segment for now. Yeah.
Did you just say whatever Calcite can do? I'm sorry if I got that.
That's the front end.
Calcite is the yeah.
How does it compare to Ready Set? You know, Ready Set?
Yeah, I think they essentially, so they wrote some papers about it. It was called something else. They are really optimized for web.
Yes.
Essentially, you could think of it as a caching mechanism than incrementalizing queries. And they maybe have a much narrower range of queries. I think it's a completely different market segment. So I don't think they have a general theory of incrementalizing arbitrary query. Scientifically, that's the short answer. But I don't think we compete. That's the market answer.
The model is different too, because when you're ready set, like the application runs the query, and then they compute on demand, like the cache is all. Where this is like it's a flow coming in there.
Yeah, so there's various program analyses that you can write in data log. Right? But for the people who are not scared of data, is there a paper that describes how to do incremental data log?
Yeah, we actually published a paper in the conference Data Log 19 about our system, and we were comparing it with and Souffle is not incremental, but it's a widely used version of Datalog. And there's this company, Logic Blocks, actually, they have an incremental version of Datalog.
They're down. They're dead.
They're dead already?
They get acquired.
Well, okay.
They get acquired and killed. And then they have the new one, relational AI.
Okay, relational AI. Yeah. So I think most people migrated to relational AI. So, well, Datalog is a very simple language and very resistant to change, like doing group by kind of stuff. Nested collections, very hard in Datalog. There's no good syntax. And we had very powerful user-defined functions. So you could essentially lift those functions to collections. And those you could write in a Rust-like language. So it was very powerful, Turing complete using arbitrary loops. So it was very rich Datalog. So it was very practical. They deployed the product, but still nobody would want to learn it.
Mihai, I have a question. I don't know if you can hear me.
Yeah.
I think this was great. I think the Z-sets idea the Z-sets emphasis that you made totally makes a ton of sense. Cleans up a lot of what people have thought of before. So 2 parts of the question. Have you looked at, there was a time in the database community where people are looking at streaming database systems and looking at rethinking how operators work. There was the symmetric hash join and things of that sort. When you implement this, do you use ideas like that? Or like, what does your runtime infrastructure look like from the operator perspective? Or are you just piggybacking to vanilla SQL operators, or you have specialized operators to do things more efficiently for your environment?
So our runtime is entirely handwritten in Rust from scratch. So we try to use clever algorithms. So you use B-trees for storing these integrals. Locality is very important. We tried several algorithms. We have blue filters for fast lookup for the read path. So you have to learn from, I'm not sure we have done everything we could. We're a small group, and funny enough, none of us is a database person. So we're learning on the fly. But many of these are good system design principles, I think. So
Great. And the second part is you have a ton of operators. Obviously, there are applications of this for maintaining dashboards and things of that sort. But as you look at more ETL pipelines, maybe feeding into ML or AI pipelines, do you see a different type of compute structure, different types of operators? You did mention some UDF. So I was wondering if you could elaborate on that a little bit.
Yeah, so we have a web page where we have a bunch of demos. Some of them are actually for data enrichment for ML pipelines. We don't do any proper ML ourselves, and we pride ourselves in it to some degree. Although we say on the front page AI and ML we have to. But so as I said, the data I mentioned briefly at some point that there's three personalities this engine has. One is for ETL kind of queries, proper incremental view maintenance. Another one is for stream computation like Flink type stuff, where I think we can clean up. Flink doesn't have a semantics. We can give a semantics to what Flink is doing using the stream abstraction. And we understand much, but now we can prove the correctness of everything we do. We have a spec. And third is recursive queries and graph queries. So we can do, for example, transitive closure of a graph incrementally, which differential data flow could do too. So you compute the closure, then you add insert edges, and we will incrementally change what's the transitive closure of the graph. And we can do very complicated graph queries.
It's great.
In SQL.
So you hinted at the beginning, there were 4 operators you only tell us about 2. The other 2 you said were for fixed point computations. What were they?
Yes, so these operators are enough to do SQL, but what you cannot do is a recursion. So if you have a view that depends on the previous version of itself, SQL allows you to do that. So the way you do it is actually these 2 missing operators are trivial. One is an introduction and one is an elimination operator. One creates a stream out of a scalar, and the stream is the input scalar followed by zeros. And the other one is well-defined only for streams that are 0 almost everywhere. So it means they have only finite number of non-zero elements. And this adds up everything in the stream. So this assumes a stream and gives you back a scalar. So now with these 2 extra operators, turns out you can write circuits where you input a scalar, then you iterate, you produce a stream. The stream is essentially iterations of a function that you want to compute. And when you reach a fixed point, you stop and you emit the result using these 2 operators. And that's how you can do recursion. And now we have a beautiful theorem which says you can lift these operators by lifting each individual operator separately. And that's how we can do incremental recursive queries. The same algorithm works for that. That's it. It's very, very simple mathematically. And implementation is also very simple. But that's the 2 operators I have shown you.
What about lateral joins?
Well, lateral joins, as I said, today we rely on the decorrelation engine from Calcite, which is a little deficient. So some of them it can do, some of them it can't. So in principle, it could be done. In practice, we have all that.
That's what I was going to. I don't know if counts. I can't decode it all. So like, if it comes out, and you see the lateral join. You basically can't increment.
That's correct. So I think every query engine will have some shortcomings like that. So the theory will work. The practice is, I spend almost half of my time on Calcite, so reviewing and so Calcite seemed to me a little moribund a couple of years ago because they have like 400 pull requests that nobody has reviewed.
Yeah.
So I spend a lot of my time reviewing pull requests these days. So this has brought some new people who are actually fixing bugs. So
Within Calcite?
Yeah. So
you said you're committed to Calcite now?
I'm a PMC member now.
Oh, okay.
Calcite, yeah. Well, nice from the outside, maybe. So I think it's getting better.
And so you use Calcite and then for the execution and data storage module.
The runtime is entirely Rust. Yeah, the runtime has several pieces.
There must be split to disk as well in case there needs.
Yes, we have spilled to disk. We have spilled to S3 to EBS to local NVM. We have a bunch of. So let me see where. Now this is a fault tolerance part. So another thing which is just very nice is that because there's one operator with state, this is the one you have to checkpoint. So if you checkpoint this, all the instances of this operator in your pipeline, you're done. You have fault tolerance. So the compiler, there's several libraries. So this is the compiler structure. We do as little possible in calculate, and then we move to our own IR. And then in Rust, you have user-defined functions. You have the SQL runtime library, which implements the semantics of SQL, which the null has very bizarre semantics. And we have the core library for operators. When is my next meeting?
1:30, but
Alright.
it's technically with me, I think.
Okay, great. And then we have this adapters library to talk to the outside world. These are all handwritten in Rust. And then nobody asked about this, but this is the slowest part of the system. So we used to generate code that wouldn't compile in 1 hour. The Rust compiler is terrible. So this theory, actually, if you look at it, it's beautifully generic. Everything is generic in all the types. There's generics with 6 nested parentheses. So, and then Rust chooses to monomorphize everything. So it generates a separate copy of the implementation for every combination of types you could have. And you have collections that are 200 wide, It can generate easily millions of lines of LLVM code. Yeah.
And the DBSP optimizer, that's in Rust as well.
No, this is all Java because
This is all Java.
it's a call side side.
So you're doing Rust code gen in Java.
Yeah. So I know this was a good idea. Normally, if your query runs for a very long time, it's a good trade-off.
Yes.
Compile queries. Compile queries in general, I don't think they were very successful. Even the C++ compiler is slow. Maybe in Go.
Yes, same matter. So you're saying one single query takes an hour to compile in Rust?
No, this is hundreds of years. We
Okay,
compile-
okay.
So we have multi-input, multi-output pipelines. They are called pipelines.
Got it, okay. Okay.
1 hour, 1 period.
I mean, yeah, considering how fast it'll be after you've done it. And you have to do it once, right?
No, in the debug cycle, you have to do it all the time. People hate it. So we did a lot of stuff. We essentially tried to hide the types from the Rust compiler.
Yeah.
And we also split into many small crates. The blog post now we generate 1,000 different crates, and suddenly the population went down from 1 hour to
Those
2.
dependencies probably went away.
No, I don't know what the compiler is solid. It's a sick compiler. They just don't care about this. In my speed. But on the other hand, we've never had a bug like a crash, a memory-related crash or a panic that we didn't expect. So the thread safety and the memory safety is just amazing.
Yeah.
So there's benefits to us. And I'm not sure it was the wrong choice yet. We'll have to see. Well, probably, the way to do it is JIT. So that everybody does JITs. If you have enough resources, you will build a JIT too.
Okay, awesome. Thank you.